Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. What about, have you got a little story?
Well, I saw an interesting story. Apparently some Dutch scientists have been growing pork, not in the conventional way, by getting a pig and chopping it up. What they've been doing is growing pork in a dish, basically.
Bizarre, how they've been doing that?
So they've been basically getting some pig embryos, waiting till they divide a bit and get the cells, which are going to turn into muscle cells, and then grow them up. And the advantage is that from one pig embryo, you can, in theory, they can't do it at the moment because it doesn't quite work. But you could get sort of thousands of pigs' worth of meat out of it because it will just keep on growing and growing and growing.
I should ban you with this stuff because I don't eat meat. That sounds disgusting.
Well, you see, the idea is that then
yes.
you can eat meat without all of the traumas of killing the animals.
You'll be still taking their embryo, though. It's oh dear.
And also, it's much better for the environment because if you grow a whole animal, there's lots of bits we don't eat. The animal spends a long time running around, using up lots of energy. So if you grew meat in dishes, some people estimate it might save 80% on the energy. So it'd be much more efficient and better for the environment. But they haven't really got it working yet. At the moment, it's kind of a bit floppy and soggy.
Oh, no.
They reckon they need to exercise their muscle cells, so they're working on ways of electrically stimulating them so as they get some exercise. And they'll probably get a lot tougher and a lot stronger and more like real meat.
Anyway, let's go to our first lot of questions. Michael has sent an email in to say, what about, Dr. Dave, if you had a sphere made of one-way mirror, light could get in but never get back out, would it trap light energy? And could he have a patent of that if it would work?
If you could make a one-way mirror in the way he is thinking you could make it, then it would trap light. The problem is you can't. That's not how one-way mirrors work. If you've ever looked out of the window at night, all you can see is your own reflection.
Yeah.
Because outside is really dark and glass reflects maybe 10% of the light which hits it. And so all you can see is a reflection. If you look out during the day, you can see everything outside really well because outside's brighter than where you are. Mm-hmm. So the reflection's really dim in comparison. One-way mirrors work exactly the same way, but the mirrors reflect maybe 80% of the light. So that if you sit somewhere really dark and the other people in a really well-lit room, you can see the light which gets through from them, but you can't see your own reflection because you're in pitch blackness, so there's no reflection. You can't really make a gate which only lets light in one way and won't let it out. So it wouldn't work for actually some really quite fundamental reasons of physics, because essentially that if you could get something which would let light in one way and wouldn't let it out, you could get a sphere which would get hotter and hotter and hotter, and then you could basically make a perpetual motion machine by running a heat engine from that and generating electricity from the heat engine and powering a light bulb from that. And that's not allowed and that just doesn't work due to all the physics we know. So if you could get a proper one-way mirror like he's thinking of, it would work fine. Unfortunately, I think they're impossible.
What about, though, if you put another set of mirrors inside to reflect it back, so you'd have a trapped sort of donut type idea?
The problem is if light can get into something, it can always get out of it. Which means that you can, and also mirrors can, and there's no such thing as a perfect mirror. You can get to about 99.9 a few times % efficiency. But if you had two mirrors and bounce light between the two of them, it goes so fast that it's bounced back and forth so many times that it would have decayed very quickly.
Well, let's go straight to the phones now. We've got Roy on the line. Hello, Roy.
Good evening, Sue.
How are you?
Very well, thank you.
What's your inquiring mind after the answer to?
I'd like to ask Dr. Dave. We're told that the most environmentally friendly fuel for cars is hydrogen, as the emissions are water. And I'm wondering whether we could have hydrogen fuel power stations.
That's a very good question, Roy. Yes, if we had a source of hydrogen.
The
problem is that if there was a big vat of hydrogen, or you found that you could dig it out of the ground, then it would be a wonderful fuel, and all it would produce is water as a byproduct, waste product. The only problem is hydrogen, there's none of it free on the Earth. You can't find it lying around, you can't dig it up anywhere, so you have to make it from something. And the most common way of making hydrogen at the moment is by taking natural gas and doing various chemistry bits with it, I think reacting it possibly with water when it's very hot. And that produces carbon dioxide and water and hydrogen. And so you can get hydrogen like that, which is great, but you're also producing the carbon dioxide, so that's not ideal. You can also produce it by putting electric current through water. It's called electrolysis. You might have done it at school. If you just pass electric current through water, the hydrogen comes off at one electrode and oxygen comes off at the other one. Problem is that uses lots of energy, and you've got to get that energy from somewhere. And so you'd need, if you were going to run all your cars on hydrogen, you'd need lots of extra power stations, which are to generate the power to make the hydrogen.
I see.
So you could use, I mean, it would actually be a very good use of wind power, because you're not too bothered about when the power is produced, because wind is a very kind of on-off sort of power. Sometimes there's lots of it, and other times there's not very much. So it would be a great use of wind power if you had lots of wind turbines, because when there's lots of wind, you can make lots of hydrogen, and when there wasn't, you could leave it for a bit. Hydrogen actually is only a really effective, it's a very good battery. It's not really a source of energy on the Earth.
I see. All right, thanks very much.
Thanks.
All right, nice to hear from you, Roy. Thank you very much.
Bye.
Now, white bread is it this colour naturally, or do the makers put additives in it to make it like this? Also, why when you burn toast, why does it go black? You should need to turn your toaster down, obviously, that's scientific, but why does it?
Bread is made out of wheat, and the seeds of wheat, so a grain of wheat. There's various bits to it. Mm-hmm. There's a thing called the endosperm, which is the fuel for the growing wheat plant, and that's actually just white. It's basically starch, and that's what you make white bread from. If there's also things like the wheat germ, which is the embryo of the wheat, which has got lots of protein in it, and there's some husk, which has got lots of fibre in it. White bread is not additives. It's just taking away all the husks and all the husk and the wheat germ. Mm-hmm. Wholemeal bread has got the whole of the meal, including the wheat germ, which has got the protein in it, so it's better for you, and the bran, which has got lots of fibre in it. So there's a lot more stuff in brown bread, which is why it kind of feels like, I always think there's a lot more to it when you eat it. So the white is perfectly natural. It's just by taking out all the coloured bits of the flour, you're left with white flour. White goes black when you overcook it. Starch is basically lots and lots of sugar molecules all chemically glued together in great big long lines. If a sugar is a carbohydrate, so it's basically got carbon and water in it, carbon, hydrate, water. Mm-hmm. So it's water and carbon reacted together in a special structure. And if you heat it up really hot, you drive off the water, and the first thing you actually produce is sort of caramel, which is sugar molecules joining together in different ways and driving off some of the water, which is why it goes brown to start with, and it tastes quite good. Also tastes good because there's some protein in there, and the sugars react with the protein, a thing called the Maillard reaction, which produces really nice tasting sort of fried tastes. And then if you cook it even harder, you drive off all the water, and all you're left with is the carbon from the carbohydrate, and carbon is soot, it's black.
Right. Now, Dave from Great Yarmouth, he says he hears very often that genes are found responsible for many diseases, but in reality there is very much more illness and disease around. There seems to be no cures as prophesied, and huge amounts of money go into research. Should we believe all the data, or are we looking in the wrong direction regarding areas of science?
It's not my specific area, but I think the fundamental problem is that humans, for any living thing, is just atrociously, immensely, ridiculously complicated. I mean, if you imagine a computer and computer chips, they're the most complicated things which humans have ever built. But a single living cell is far more complicated than the biggest computer chip, than the most expensive, complicated computer chip we've ever come up with. Mm-hmm. And it's also not. It hasn't been designed. It's not designed it's not designed for maintenance. There's no instruction manual, and it's been evolved. So it's a bit like a crazy sort of someone who will do basically evolution will do whatever works now. So you get all sorts of crazy, slightly bizarre design decisions which make sense for that generation of animals because more of them survive. But at 10 million years' time, it kind of is a bit crazy, and then they do another kind of kludge. You evolve another kludge to overcome the first problem produced by the first kludge. And so, it's just life is incredibly, incredibly complicated. And so it's difficult, basically. And I'm a physicist. I don't know an awful lot about biology. I know enough to know that it's hideously complicated. And I think 50 years ago, we didn't know how complicated life was. And so people were overly optimistic about how easy it was to cure things, because we have cured a lot of things like bacteria. Antibiotics have saved millions of lives. Vaccines have saved probably more lives than that. Have wiped out all sorts of infectious diseases. But the problem is, if you stop people dying this week, then they're alive next week, and the next year, and the next year, and they get older and older. And as the older people get, then they just start wearing out. And then you've got to try and, rather than just stopping things which kill you, you've got to start mending things which are broken, which is another degree. It's a whole lot more difficult. And so it's just a very, very, very difficult problem.
It's getting scary that we're growing meat in dishes, that's all I can say. Anyway, let's go to the phones. We should have Tony there. Hello, Tony.
Good evening, madam.
Oh, hello. How are you? Lovely to hear you.
Fine, lovely, and you, dear.
All right, Tony, what's your question?
You know, these atomic bombs and all the rest of this nonsense, they're not very big for the damage they can do.
Yeah.
But let's say a bomb is just 3 metres long. Would they ever, do you think, be able to miniaturise it so it was only 3 millimetres long? And on the same ratio, it would still do a hell of a lot of damage.
Certainly with conventional nuclear bombs, you do really, certainly using plutonium or uranium. The way nuclear bombs work is that you've taken an element like plutonium, which is unstable, and if it can split in half, that releases a lot of energy. Mm-hmm. And when it splits in half, it releases some things called neutrons, which are some subatomic particles which make up the nucleus. And then those can fly off and then bash into another nucleus and cause it to split and release more energy. And then the split hits some more and release more and more and more and more. So you get a chain reaction and you get an immense amount of energy released. The problem is you need it to be a certain size so that for every 1 neutron you produce in a reaction, it produces causes another at least 1 more nucleus to split. So the chain keeps on going. If it only causes on average half a nucleus to split, then it sort of fizzles and it doesn't explode because you throw in 30 neutrons. The next generation you only got 15. The next generation you've only got 7, so on until you've got none left. You want it to go from 15 to 30 to 60 to 120, so it keeps on getting, so you get more and more reactions and you get more and more energy released and you get an explosion. So if you make it very, very small, what tends to happen is you lose a lot of neutrons out the side. So you there's a limit to how small you can make a nuclear bomb with conventionally, because you just lose all the neutrons and it just doesn't go bang.
Which makes me very pleased.
It is. The Americans have built one which will fit in a rucksack. I think it was probably weighed about 50 pounds. And I think it produced the equivalent explosion of about 25 tons of dynamite or TNT. Yeah. As far as I know, there's no way of making one smaller than that.
Thank God for that.
Absolutely, Tony. Thank you so much, Honeybun.
Pleasure, dear.
Take care.
Have a nice evening.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Colin has sent an email in from Stevenage. Hello, Colin. He says, is it possible for the human body to be colder than the environment it's in? Or is it the case that the human body can only be as cold as the environment that it is in?
You do have various ways of cooling yourself. You try and keep your body at 37 degrees centigrade. The major way of cooling yourself, one of them is if the air temperature around you is below body temperature, you can send lots of blood to your skin, which is why if you do lots of running, then your face often goes red because your body's sending lots of blood to your skin. So when the air rushes past it, it cools it down. The other major one is sweating. If you sweat when the water evaporates, that can lose heat, even if the environment is hotter than you are, as long as it's dry. So humans can survive perfectly happily in deserts out in the 40 degrees centigrade, 50 degrees centigrade. I think it's unpleasant. But as long as the air is very dry, sweating is very effective. And you can lose lots of heat that way, and your body can stay below the environment temperature. However, if it's very, very humid, sort of in a hot, steamy environment, then the water doesn't evaporate because the air's already full of water. And so you can't lose much heat by sweating. And then if you can't sweat and the air's hotter than you are, then you've got no way of losing heat and you will overheat and it will cause you big problems.
Adrian has sent a text in saying, Sue, can you make your own bullets using custard powder? Can you ask the Naked Scientist, please? Why do you want to make bullets out of custard powder? Go on. What do you reckon, Dave?
I don't know about making bullets. I've never heard of anyone trying to make bullets out of custard powder. I mean, you could, if you crush together, if you can shoot anything you like out of a gun. I don't know why you'd want to shoot custard powder out of a gun. It would fly outwards. What you can do is burn custard powder, and it will kind of burn really well. It burns as well as petrol if you can mix it with air well enough. We've got an experiment on the website where I blew out of a sort of pipe thing a load of custard powder into a flame. When I blow it out of the pipe, it mixes it with air really well. When it hits the flame, it ignites, and you can form a sort of 2-3 foot fireball like this.
Don't try that at home, please.
No, don't try that at home. I almost lost my eyebrows quite well doing it once.
Did you? I thought it was a bit trim,
just
actually.
far enough away, but it's fine. You can shoot virtually anything out of a gun if you put enough gunpowder behind it, but I don't know why you want to shoot custard powder out.
No. Please don't do that, Adrian, if you wouldn't mind. Mike in Colchester says he's off to Borneo, the land of shrunken heads, for Christmas, and wondered, how do they shrink the heads? As surely the skull, which is made of bone, would be a stumbling block. Good question.
It is a very good question. It's probably another one which will make your flesh creep.
Oh, will it? Oh, dear. Go on.
There's various tribes, I think, in bits of the Pacific and the Amazonian basin did this. Basically, they want to shrink the heads, and he's right, the skull does get in the way, so you have to take the skull out of the head.
No.
So they take the skull out of the head, and they take out the brain and any flesh inside. And then essentially they tan it. They add a load of tanning, they turn it into leather. Which preserves it, and then they dry it out and they kind of deliberately shape it so the skin has still got some shape. And so yes, and as it dries out, it will shrink. And the reason why the skull isn't a problem is they've already taken it out.
Thank you for that.
A bit unpleasant.
Let's go to something a bit more cheerful now, shall we? There's another little number here, an email actually from Derek in Wellingborough. He says, how is gold formed and how does it end up in rivers and streams where people pan for gold? Or is that just on the Western movies?
Okay, how is gold formed? Gold is an element, and therefore it has to be made in some kind of nuclear process. It's actually made it's a very, very heavy element, and all the heavy elements are actually made in exploding stars called supernovae. Really, really big stars, bigger than the sun. When they get to the end of their life, their core collapses and forms either what's called a neutron star, which is basically a huge atomic nucleus with the same mass of a star. And when this does, a huge amount of energy is released, and it causes a huge explosion. And this energy can create heavy elements. And so any elements heavier than certainly iron are made in supernovae and other big stars. So any gold you've got on in your rings was made in a huge exploding star, and then that got thrown out from these stars, and some of that was in the stuff which made up our solar system. Some of the stuff which made up the solar system made up the Earth. Lots of the light things like hydrogen and helium got blown away by the sun. And so all you're left with the heavier stuff, and then the gold is a lot of it is probably a lot more gold in the centre of the Earth, but some of it some of it's mixed around all over the place, and it's in some rocks. It happens to be concentrated, and you can find little lumps of it.
if you're lucky. On to the phones now. We've got Janina. Hello.
Hello, darling.
How are you? Yeah, I'm very good. All right, you're through to Dr. Dave. What's your question?
Right, it's a bit of a spooky one for you.
Okay.
We have a touch lamp in our bedroom, and it's one of those, obviously, where you touch it on and off. Now, we've been noticing that it's been coming on and off, even though it hasn't been touching anything apart from the wooden surface that it's on, all by itself. For the last 2 months, it's been doing this. We actually started wondering whether we'd got ghosts in the house.
Cosmic.
I know, we started wondering. But then we had a bit of a coincidence thing happen. My daughter, in her bedroom, turned on her fan because we'd told her to turn it. Actually, no, it was off, sorry. Because we'd said to her, can you turn your fan off? Because you were in the bedroom. You didn't need it on because it was, we didn't want her to waste electric. Mm-hmm. And we realised that she'd done that before, and it had actually come on the lamp.
I had something very, very similar. We had one in our bedroom. Whenever we turned on the main light in the room, the lamp would turn on. Or sometimes it would, sometimes it wouldn't. And that confused me for a while. Until I noticed that we got a clock radio by the bed, and the aerial was going up to. I tied the aerial onto the lampshade, and it was an energy-saving light bulb.
Right.
And I think what was happening is whenever you turned on the energy-saving light bulb, they have a load of circuitry to produce quite high voltages inside to start a spark inside the tubes, which actually generates the light in an energy-saving light bulb. And that was inducing electricity to run up and down the aerial of the radio. And that was quite close to the touch light. And the touch lights work electrically. They on the surface is slightly conducting, and they apply a very rapidly changing electric field to the surface. And when you put your finger near it, that changes the amount of current which goes into this rapidly which moves in and out of the sphere. And so in some senses, some of the current is flowing through your hand, and so it can detect your hand. And so if you produce a rapidly changing current in a wire near it, it can think, there's a hand there, and it will turn on. So the fan turning on and off next door is probably producing a whole lot of current in something near your touch light, or possibly even just down the mains.
All right, well, keep us posted anyway, and maybe Dr. Dave might
try moving it, or trying a different power socket and see whether it does the same thing would be a start.
Maybe a power surge socket or something.
Actually, though I don't know if you've seen the things you get for computers to reduce power surges.
I have seen them, yes.
Yeah, just purely for interest value, it would be interesting to try plugging one of those definitely into the TV,
right?
Or the especially if you can borrow one or something, and see whether it reduces the problem.
Thank you very much, Janina.
Thank you, darling.
All right,
care.
You take care. Bye-bye. Bye-bye. Mark in Bletchley says, could you ask Dr. Dave, why do electrical appliances arc blue? Like, I live near the railway line, and the overheads all arc blue as they go along. My toaster does that as well, Dr. Dave.
If your toaster's arcing blue, then I think you need a new toaster.
It's a new toaster. It's only if I press the cancel, button, he goes... Not a big one, but I can see it inside and think,
Sounds worrying. I guess it probably could be the switch not being quite perfect. Yeah. Basically, what happens in an arc is you get electricity flowing through the air. That gives air molecules a huge amount of energy, and they give it out. Now, I don't know if you ever did flame tests at school, where you got a little wire, dipped it in some various chemicals, and then put it into a Bunsen burner. And you get different colours coming off the wire. Yeah, if you remember that at school. And different elements make different colours. Also, if different metals make different colours. And also neon tubes. And neon makes red. Neon tubes are red. Mm-hmm. Sodium makes bright orange, as sodium in street lights, why that's yellow.
Yep.
And nitrogen happens to be a pale blue colour. If you give it lots of energy, it gives out pale blue light. And so sparks give air huge amounts of energy, and it gives it out as blue light. Some of it as blue light.
All right. A question for Dr. Dave from Steve, who says, can the process of electrolysis be reversed to manufacture water from oxygen, hydrogen? What are the dangers?
Simple answer is yes. The easiest way to generate water from hydrogen and oxygen is to set fire to them. Then the hydrogen burns in oxygen, forming H2O water. You can do that in an engine and get some of the energy out. It's probably, but car engines are only fairly inefficient, only 30% efficient maybe, so that wastes 2/3 of it. It's much better to do it in what's called a fuel cell, which is actually just an electrolysis rig which is running the other way, where you pump in hydrogen and oxygen, and the same cell actually produces electric current out. And you can get electricity out and with water as an effluent. So that's what all the hydrogen fuel cells, which you may have heard about on various bits of science news, are trying to do. Basically run electrolysis backwards.
Mm-hmm. Helen in Cambridge says, why is it that she cannot see the stars?
Probably, I don't know if she's living in Cambridge. The biggest reason why you can't see stars at the moment is probably the street lighting. It's a big problem for astronomers, actually. It's the reason why no serious astronomy is really done in this country anymore. If you're at night, lots of street lights, lots of people's outside lights, they give off light, it goes up into the sky. Any dust or something in the sky will bounce it back down. So if you look up, the sky isn't properly black anymore, and the just general background haze reflecting the street lights back down is so bright you can't see the stars. If you go to somewhere in the middle of nowhere, up in the Lake District, or I grew up in South Devon on the coast, you can still see lots and lots of stars on a good dark night in the winter.
All right, well, let's go to the phones now, because we've got Idwell on the phone. Hello.
Hello.
Oh, hello. Sorry about that. Got you on the wrong thing. All right, very quickly, because we're fast running out of time.
If you set diesel on fire and try and pour water on it, it flares up. Why can't they make diesel vehicles with a water tank to mix it with the diesel to make the vehicle run more economically?
Oh, as in, because if you throw water on, then it looks like it's releasing lots more energy. The reason why diesel flares up when you throw water on it is that the water boils and then it spreads the diesel out all over the place. The same thing happens with the chip pan fire, and then that mixes it with the air, which means it can burn much more quickly. It's got the same amount of energy in it, and so it will get you the same distance. It's just releasing it more quickly, so it looks more impressive. So I think with some petrol engines, adding water can make them slightly more efficient, but I don't think that's true with diesel engines.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.